using the new system.
Yeah.
You log in the Zoom here.
You log Zoom.
Well, you need the computer to accept the login from this device, but you can use the tablet. And then I could disconnect the computer and this will keep working.
Hi, Paula.
Hello, Yoli. How are you doing?
Very well. Running the whole time, you know, a little bit stressed, but it's fun.
I'm checking, so you are in Granada, is that right?
Yes,
Cool.
yes. I'm here since, let's say, 4 months before the pandemic. So, yes, I'm very happy to be here, yes.
I have to show up there.
Yes. So how are you?
I'm all right. I'm here in Spain as well.
Ah, cool. Do you like?
Yeah.
Not,
So please don't insult anybody because everybody's listening here.
Yeah.
Don't criticize. You can criticize Alessandro because he's not here, but not anyone from. So I think we can start already. So thank you very much for being here. Today we have a speaker, Yolanda Jiménez Teja. She's from Cadiz. She studied mathematics, and she did after mathematics she did the PhD in the IAE in Granada. After a short postdoc there in Granada as well, she moved to Brazil for a postdoc, and she came back with a Marie Curie to Granada, where she's now working with Pepe Vilchez and Estallidos group, I guess. So, am I right?
yes.
So today she's going to talk about the intracluster light fraction across cosmic time. And so, one of you on.
So thank you very much. Thank you very much for the invitation and the warm welcome. It's always a pleasure to be remotely there at CEFCA and to talk to all of you. And this time I like to show you something that is my main work right now, although I'm diversifying a little bit right now, so I'm working in several fields at the same time. But my main work is about what is called the intracluster light, and I like to show you some results that we have obtained in the past years. But also taking the advantage that we are developing a lot of new tools for the intracluster light and for photometry and morphology of galaxies, for example. I'd like to show you also, or at least give you a little flavor of new applications that we are finding for our algorithms and techniques, especially using the recently arrived James Webb data. Well, I hope you enjoy this talk. So let's start from the beginning. What it is intracluster lights, which is going to be the main topic of the talk. So the intracluster lights is a barely studied component of the galaxy clusters. We all know that the galaxy clusters are composed by galaxies, hot gas, and darker matter primarily, but there is a fourth component that has been forgotten in the last years, at least until 2005, more or less. This is the intracluster light, which is a very diffused and faint and extended component made up by stars that are free in the sense that they are not hosted by any galaxy of the cluster, but they are bound by the gravitational potential of the cluster. So they orbit within the cluster, but they don't belong to any galaxy in particular. In this very beautiful image by Mijos, we can see the intracluster light as this orangish region which is surrounding all the galaxies in the cluster. And it's usually very faint. Many works say that it can be about 1% of the sky level, but the total amount of ICL is very important in the cluster. It is estimated that it can make up 50% of the baryonic matter of the cluster. So it is very important, but although it has been so unexplored. We can see that its relevance is connected to the hierarchical process of accretion of the cluster, because we will see that the ICL is formed joined with the different processes of formation of the cluster. So knowing about the ICL is like reading a tale on the formation, on the history of formation or an evolution of the cluster itself. Apart from that, the ICL gives us insights on the metal enrichment of the intercluster gas, and also we can derive cosmological constraints from the intracluster light and for example, its contribution to the baryon fraction in clusters. So we have a lot of, like, say, applications of the intercluster light that I'm going to name ICL from now on because it's shorter. But still, there is a lot to discover with the ICL. But where the ICL comes from, where these stars come from and end up like floating freely in the potential of the clusters. So mainly, there are like 4 mechanisms that are mainly considered when we talk about the formation or the origin of the ICL. For example, all of them are kind of violent. For example, a violent relaxation after major measures, especially with the BCG, that creates a lot of ICL, especially for redshifts higher than 1. But also other mechanisms are more important, or at least more efficient, for intermediate and low redshifts, about 0.5 and less. Like, for example, the tidal stripping of very luminous galaxies with shreds a lot of stars from the outskirts of these galaxies and through them into the ICL. Also the disruption, sometimes total disruption of dwarf galaxies into the potential of the cluster, and also surprisingly in situ star formation. I mean, there are stars that are born in the ICL, although this mechanism is very, very, let's say, not important in comparison with the other 3. There are also other mechanisms that we are proposing right now, like preprocessing in falling groups, but these are not as important as those. I'd like to show you here a very beautiful animation of how the ICL can form when we have a lot of interactions between clusters, between galaxies within the clusters, and etc. I'm going to repeat that for you. So the galaxies here would be like the darker spots there in the movie, and the ICL would be this gray envelope that is creating as galaxies are interacting more and more. As you can see, as the clusters are, let's say, virializing, the ICL becomes like better behaved, let's say, more circular, more symmetrical, etc. But at the very beginning, the ICL is full of tidal streams, a lot of features there, like plumes, loops, arcs, etc. So, for example, looking at the morphology of the ICL is a way to know in which stage, dynamically speaking, a cluster is. So, let's go to the beginning. I say that the ICL has been like forgotten for decades, although it was first seen in the 50s by Zwicky. But it has been unexplored all these decades because of two main reasons, mainly. A technical reason, that because it is very difficult to detect. I said that this is very faint. We are going into the low surface brightness universe here, so we need really very deep and high quality images to see the ICL. And also an analytical problem. It's very difficult to disentangle, to say which parts of the light that we are seeing belongs to the ICL and which part belongs to the galaxies, and it's even it's even harder when we talk about separating the light of the BCG, the brightest galaxy of the cluster, and the ICL. The reason for that is that the BCG is usually located at the center of the potential of the cluster, but it's that the ICL also is more focused in this point. So at the end, we have like two profiles there in projection, two profiles, the ICL, which is more extended, and the BCG, which would be more peaky, let's say so. And it's very difficult to see where the winds of the BCG, let's say, ends and the ICL starts. And if the BCG has an extended halo, this is even more complex. So here is a very good example to visualize how it's difficult to say where the ICL, the galaxies, which are here plotted in white, where the galaxies really end or really end their domination, their regions of domination, let's say so, and where the ICL dominated regions starts. So many people say that there is no difference between these concepts, the BCG, for example, and its extended halo, and the ICL. But we do know by dynamical studies that there is a difference, that there are indeed separate components. For example, here, looking at the velocity dispersion profile of M87, which is the BCG at the Virgo cluster, we see that the velocity dispersion is decreasing, but looking at, for example, at the planetary nebulae belonging to both to the galaxy halo and the ICL, we see a very steep increase of the velocity, which indicates that there is a different component there, dynamically speaking. So the ICL is indeed a different component from the extended halo of the BCG, although, as I said, very difficult to separate. As there are a lot of methods out there to measure the ICL, but all of them rely on different assumptions, a priori assumptions on either the properties of the ICL or the properties of the galaxies in the cluster, we decided to develop a new algorithm to measure and study the ICL without assuming anything a priori about it. We developed that in 2016, and this algorithm was called CYCLE, which stands for Cheff's Intracluster Light Estimator. In a nutshell, this is all what CYCLE does. let's look at it step by step. The first thing that cycle does is trying to remove the light of all the galaxies in the cluster that are considered easy to remove. Let's say all galaxies that are, let's say, far from the ICL, or even on the ICL dominated region, but in one of the, for example, that are lying on a ladder and on a ladder of the ICL. So it's like if we have the ICL, which is this very smooth component, and we have a bump there that is happening there because we have a galaxy. All that we do is modeling this galaxy, this bump belonging to the galaxy, and leaving the ICL there untouched. How do we model the galaxies there in the ICL? We use what it's called CHEFs, which is a tool that many of you at CEFCA know. That is a mathematical orthonormal basis composed by Chebyshev polynomials, or a derivation of Chebyshev polynomials and Fourier series, with joined together in polar coordinates, compose a basis which is very efficient, very flexible, able to model any morphology or any galaxy with any morphology, with a few components. So with this algorithm, CHEFs, we can model, for example, galaxies as complex as this one. Here you can see a original image observed by Spitzer of a very detailed nearby galaxy. And here you can see the CHEF model corresponding to this galaxy. So I'm going to go back and forward to, this is the original image, and this is the CHEF model. You can see that there are some details that are missed, mainly because these are stars. CHEFs are not able to model stars, because CHEFs are basis of let's say a mathematical space composed by functions that are smooth. So if we have a star that is saturated or with spikes or with something that is super sharp, that not belongs to the mathematical space of functions that CHEFs are able to model. So these stars are normally masked out. And this is not a problem because there are not many of them in the fields that we are usually analyzing, so that's okay. So this is a CHEF model. Using CHEFs, we go from, I don't know if you can see my pointer, I guess so, but using CHEFs, we can go, for example, from this original image of the Pandora cluster, Hubble 2744, to this image where we have modeled and removed all the galaxies using CHEFs. But for the particular case of the BCG or BCGs, as it's the case in this Pandora cluster, we have this spatial coincidence of the BCG and the ICL. So there is more difficult to separate both of them because CHEFs are going to model everything together. And CHEFs don't know where to stop the model for the BCG. So most probably, part of the ICL is going into the BCG model. So for this particular case of the BCGs, we made like a further study using a curvature map. Which is this curvature map? There are a lot of parameters to measure the curvature of a dimension in 3D. All of them very well explained in any book of differential geometry. And there is this one that is called minimum principal curvature, which is especially efficient to differentiate to know where a surface has a bump. So in the still model of this surface, we have like a bump coming toward us and like a valley that is going away from us. So for the minimum principal curvature, is kind of easy to see where the bump is happening and where the valley is dominating the region. There are numbers for the curvature where we can set the boundary between the two regions. So using this curvature parameter, we can create a map and finding the places or the points where this curvature has a highest value, because the curvature is telling us more or less about the change in the slope. So we see where the change in the slope is highest. So if we have the VCG and then we have the ICL, there is, we assume, is our only assumption, we assume that there must be a change in the slope between the two components. And this change is gonna determine the transition between the VCG and the ICL dominated regions. So in this example with the Pandora cluster, the VCG dominated regions would be outlined here with a blue curve. And we later remove the contribution of the VCG within these areas. To do that, I don't usually explain this step, but I like to explain it in more detail today, because I'm going to use this later for a new application that we have found for cycle. What we usually do to remove the contribution of the VCG within this blue outline is an interpolation. We use the pixels surrounding the VCGs to interpolate iteratively the values that we should find, let's say, behind the VCG, if we were able to separate really the VCG from the ICL. So if the VCG has outside, like, let's say, certain slope, this slope is going to be interpolated iteratively from the outside, from the outer regions of the VCG to the inner regions iteratively. This is done randomly. It's like we are throwing apertures that are covering step by step the whole region to be interpolated. And on each one of these apertures, we take like average values until everything is covered. Here in the last plot here, you can see how this interpolation works to reveal which is under the VCG, let's say so, in projection. We tested this cycle algorithm against simulations, and we found that it was super precise or super accurate. We found that obviously the more different the VCG and the ICL are, like here the VCG is super steep here in red, and the ICL is the blue component, which is much more extended. So the error that we find is super low, very close to zero. But as we go to different configurations where the VCG and the ICL resemble are more similar, like in this case where the VCG and the ICL are almost equal, then we find a maximum error of 10% in the disentanglement of the ICL and the VCG. And as we go to crazy configurations where the VCG and the ICL are, for example, here the ICL is completely embedded into the VCG, then it would be totally impossible for us to separate both of them. But well, it will be completely impossible for us and for any method, because the ICL there is not non-observable, right? We also saw, using real data, that this way of measuring the ICL is super precise. Here we can see M49, which is the BGG in Virgo, that is the brightest galaxy in a group that belongs to the Virgo cluster. And we have this study by Hart et al. In 2018, where they separate this BGG from the ICL using dynamics, using planetary nebulae. And they saw here that the radius where the ICL was dominating the image was about 50. It was probabilistically determined. If we follow these points, these measurements, the point where the measurement cross the 0.5 line of probability would be the point where the ICL starts to dominate. So it would be about, let's say, 52, 53 kiloparsecs, more or less, this crossing. And for us, we determined that the ICL was starting to dominate outside this blue curve, and the equivalent radius of this region inside was 41 kiloparsecs, sorry, which is very similar to what we find. But even more, we found that that in this work they found an excess of bright planetary nebulae in two quadrants which were consistent with the quadrants where we found a brighter ICL. So this was super surprising or super shocking, because many or all the works, the previous works working with ICL usually show ICL distributions which are completely symmetric and circular. They haven't got like patches where the ICL is brighter or not. And in our case, we found these different regions, and they were totally consistent with what was found using dynamics. So, and we were using just an image, let's say, photometry. So that was a huge success for cycle and for ICL studies. Well, I'm talking about cycle and how it performs. So I like to show you here colored image, which is also nicer than single filter images, as I shown before with the Pandora cluster. So this is a colored image of how cycle performs. This is the cluster WHL. Sorry, I don't remember the number, and it's kind of hidden here, but all this zoom thing. But okay, 0137. Okay, WHL 0137. Here in the left, you can see the original image as observed by Hubble. And on the right, you can see the image after having all the galaxies removed by cycle. So this light here would be the ICL. Now that we knew that cycle was working so well. We decided to measure the ICL, and in particular a parameter which is called the ICL fraction, which is the ratio of the ICL to the total luminosity of the cluster, that is ICL plus galaxies, in a significant sample of clusters. All of them had something in particular or in common, that was that all of them were observed by HST, by the Hubble telescope. All of them had did imaging, and all of them had their dynamical stages well defined by other proofs: X-rays, dynamics, the presence of tidal features, presence of radio halos or radio relics, a lot of different proofs, and we put them all together. So we divided our sample into merging or active clusters and virialized or relaxed clusters. And we measured the ICL in different bands, which is something that is not usually done. Usually the ICL is measured in one or at most two bands, but we like it to have like a more or panchromatic or nearly panchromatic view of the ICL, at least in the optical range. And also, we measure total ICL fractions. That is, we measure the ICL up to the level where we can detect it. We didn't measure the ICL in fixed apertures as it was done before. And that's what we found. We found here that we have a sample of merging clusters, which are the red symbols there, and a subsample of relaxed clusters, which are the blue markers there. And we found that, in general, ICL fractions measured for merging clusters were higher than those measures for relaxed clusters. That was explained because the main mechanisms of formation of ICL for merging clusters were violent, like interactions between galaxies and with the other cluster, and groups in falling, etc. While for relaxed clusters, the main mechanism of injection of stars into the ICL is passive. Is like as galaxies evolve toward the center of the potential of the cluster, they are losing ICL by ramp pressure 3p, for example, and these mechanisms feed the ICL, but in a very slowly way. Moreover, the fact that the ICL fraction is nearly constant within the error bars for all relaxed clusters implied that the colors of the ICL and the colors of the galaxies, as the ICL fraction is the ratio more or less between them two, that implies that the colors of the ICL and the galaxies of the clusters are nearly the same or are very similar, implying that this ICL comes primarily from these galaxy clusters. However, for merging clusters, we see this peak that we are going, or this excess in the ICL fractions measured in a certain wavelength range, where this excess was completely related to the type of galaxies that were throwing violently during the merger event these stars into the ICL. So, looking into the literature, we saw that in the ICL of these clusters, there was an excess of A and F type stars that was detected. We saw that this excess of this kind of stars was reflected in this peak into the ICL fraction. This was done using clash frontier fields RELICS clusters with an intermediate redshift between 0.18 and 0.56. But later we decided to explore other redshift intervals. And for example, using data from our beloved J+ survey, images, particularly from the coma cluster, we saw that this peak, this excess in the ICL fraction also appeared at lower redshift. So it seems, it made us believe or think that maybe we're seeing something that is ubiquitous, this excess in the ICL fraction, and maybe a signature of the dynamical stage of the cluster. Now, in our last work or our ongoing work, we have gone the opposite direction, where we have gone to the high redshift universe, or high redshift at least for clusters. So we analyzed some clusters between 0.8 and 1 in redshift. We also saw this feature, this peak in the ICL fraction for merging clusters, but shifted, displaced toward redder wavelengths. So it seems that the ICL fraction, as measured by cycle, in the sense that measure in several filters and using total fluxes instead of aperture photometry, is a very reliable way of determining if a cluster is relaxed or virialized. And we only use optical or infrared data, depending on the redshift, of course. We don't need to use like X-rays or dynamical studies, for example. Also, going back to WHL 0137, we calculated the ICL fractions in the infrared, which are these dark markers here for these clusters, and we saw a high excess in the intercluster light fraction at these wavelengths for this 0.5 redshift cluster. That made us believe that in general we have a population in the ICL that is mixed. Is composed primarily by red stars that are thrown there in the let's say earlier stage of the formation of the cluster, primarily for redshift higher than 1. These stars are related to the VCG, to these major measures that we talked about at the beginning of the talk, but later bluer and bluer stars are incorporated into the ICL, especially during the mergers, creating this special and significant peak that we have been talking about. So this would be the conclusions for the ICL part, and we see how this ICL fraction evolves across cosmic time and its application to know about the dynamical stage of the clusters. But I would like to tell you very briefly about another applications of the ICL that we have discovered right now and that are very exciting, at least from my point of view. And I would like to talk to you about Earendel. Who is Earendel? So here we can see again a color image of WHL 0137 that you can see that is one of my favorite systems. This was observed by the RELICS program, and this is the Hubble image. Just for fun, I'd like to show you the JWST image. Let's go back and forward. And you can see that the beauty of this new data is amazing. Which is important about this cluster? We have here, I think that you can barely see, here an arc, very long arc, that appears there because this cluster is a strong lens. So you all know that the longer the arc, the higher the magnification. So looking at this arc, we could see like several clamps there that were highly magnified by this lens, by this cluster. We discovered that there was a tiny dot here, a point that wasn't really well explained, thinking that it was a star cluster there in the arc. Looking at the lens models of these clusters, we discovered that there was a caustic. You all know that caustic are the lines or the curves where the magnification of the lens is higher or highest. We saw that one of these caustics was passing exactly over this dot. Doing a lot of calculations about the magnification of this point, of this source, and the size that this source should have not in the plane of the lens, but in the plane of the source, the original plane, which is located at redshift 6.2. This arc is a galaxy stretched, but this galaxy is indeed at redshift 6.2. We discovered that this point should have a magnification higher than 4,000, which is a lot. And measuring its size, its original size in the plane of the source, we saw that it was too small to be a star cluster. So it must be a single star, a single lens star, or at most a binary system. If it were a single star, it should have a temperature between 30,000 and 16,000 Kelvin, and each about 50 to 100 solar masses. This was the discovery was made with Hubble, and we published this thing in Nature. We have also now web images of this star, which was named Earendel, that means morning star, because it belongs to the let's say the origins of our universe. This is the farthest star observed until now. I'm pretty sure that with Webb, many other single stars farther away are going to be discovered, but until now, this is the farthest star ever known. We have just published another paper about that in APJ Letters with the new web data, and you will be thinking, what this has to do with the ICL? Well, the ICL played a very important role in the discovery of Earendel, because we really needed to know the mass density of all the stars in the line of sight up to Earendel. We needed to know this quantity. Why did we need to know that? Well, previously lens star discovery, there are a few stars discovered in this way using lenses, but all of them at lower redshifts. These stars were identified where the magnification of this bright was temporarily increased by the stars that are in the line of sight between us and these stars. These intermediate stars between us and the lens stars act as microlenses, which boosts the magnification and the bright of the lens stars. So and these boosts in the bright of the star depends on the number density of the stars that are between us. And we needed to know that because all the previous stars discovered were transient. They were discovered because of these boosts in the magnification. So we measure, using our algorithms, we measure the ICL in the surroundings in these very tiny regions around the arc, which is masked here in this image, and in particular being around Earendel. And we measure the ICL there, we measure the surface brightness of the ICL there. From that, we derive the mass, and surprisingly, we found that the running microlensing simulations, inputting this number of the mass density as derived by cycle, we found that Earendel shouldn't be a transient, but its flux and its magnification should remain the same for a longer period of time. That was super unlikely. And it was very difficult to really believe that. But time gives us the reason. So we have measured the flux of Earendel. Here I show the results for 2 years and a half apart, but we have the numbers for 8 years, and its flux has remained also almost the same, not almost the same, but almost the same within the factor that we determined that it was to change at maximum. So that's very happy news, because Earendel is unique in its kind, and we are going to see Earendel for a lot of years still. So there is plenty of science there to do. Also, we measure. I told you that we have now wave images of Earendel. We needed to study them, to analyze them, and one of the more simple things that we must do was measuring the flux of Earendel, measuring the photometry. Well, measuring the photometry is a challenge in general with James Webb. There are lots of detail, there are lots of things happening in the images, in the new images, as you have seen. It's very difficult to measure the photometry of any object in Webb images. But for Earendel, it was a special challenge in the sense that we needed to measure the the flux of this point, which is lying on the arc, which is the host galaxy where Earendel belongs. Sorry. We also have here intracluster light all around this region, and we also have the contamination of nearby galaxies as this one. So it was very difficult to measure the photometry there. If we put an aperture there, measurements were very contaminated. If we tried to estimate the contribution of the arc, that was very hard too. And everything that we tried was let's say, inconclusive. So we found a new way to measure the photometry for this very particular case, which was instead of trying to model Earendel or putting an aperture here, why don't we interpolate everything around but Earendel using, do you remember this last step of cycle, which was able to interpolate the ICL behind the VCG iteratively, well, that was what we done. That was what we did to measure Erendel's flux in James Webb. So first, we detected which pixels really belong to Erendel. For that, we really needed to use noise chisel, which you all know by Mohammed, right? Because we were unable to separate the pixels belonging to Erendel using substructure. But here you can see the clamps map as derived by noise chisel and segment. And you can see how Erendel has their pixels, their region of influence well defined. Here you can see in the bottom right, you can see the result of interpolating everything which is around Erendel within the region dominated by Erendel. I mean, within these white pixels here inside the green circle. So as you can see, the arc is not reconstructed, the arc is interpolated, as well as all the intracluster light, sky, and everything. And the flux of Erendel was measured in the difference between the original image and the interpolated image. That also has is very convenient because we minimize the impact, for example, of the sky in the measurements of the photometry. And just to finish, a new work that we have just submitted, and it was posted on Archive, I think that last week, that is about the discovery of a possible galaxy merger at redshift 11, 10 years ago with Hubble. Danko saw that there was a triply lensed image of a galaxy in this cluster. They determined that its redshift should be 11. Now with Webb, we discover that this is not a single galaxy, but it might be two galaxies. There we see two clamps there. We don't know if they are two clamps belonging to the same galaxy, or maybe two galaxies interacting. Measuring a lot of things, we are prone to believe that these are two galaxies interacting. Moreover, we discover a third galaxy there that appears in the three lensed multiple images, and that is probably going to interact with these two. And the funny thing about this was, again, measuring the photometry in these images, especially in Webb, where the two clamps appear better resolved, right? So here I would like to show you how chefs work measuring the photometry for these two clamps. This is a color composite image using all the wave filters that we have. You can see here the three clamps, or the three probable galaxies. And you can see that the chef's models are able to recover all the features of these tiny clamps, and also that we can see some kind of structures around the clamps. So we can see that they are not single points at all, but they are extended sources as observed by Webb. Well, you can see here that the residuals are very good because they respect, let's say, the wings of these nearby galaxies, and also all the ICL there. Well, we have just submitted this new finding that is super exciting. Well, thank you very much for listening to this talk and for the invitation. Thanks a lot.
Okay, thank you so much, Yoli. So, is there any questions? There's multiple. So, Elena.
Thank you, Yoli. This is Elena Dominguez speaking. We met in Granada a few weeks ago. This is an amazing job, very interesting. That's the work you've done at different redshifts and so on. I have a question related with the cluster where you show there's a mass star, and I could see something that may be the excess of the starlight. The previous one, the one that there is a gap. There's a hole at the beginning. I think it was the second cluster you saw.
Second cluster, but one of the wave images?
No. The one you couldn't read the name. This one, exactly.
Here.
Could it be, I see kind of a structure in the upper right corner. Could that be still the remnants of the star, which is not well masked? And if so, could that affect the excess of F-star light that you see?
Yes, so as I said at the beginning, stars must be masked. We have a very hard time with stars and the ICL. It's very difficult to separate them both. And chefs effectively don't do that. In this case, I think that it's not only a matter of the excess of the star, of the spike of the star here, but there is something also related to the image. There was some excess of light in this quadrant that is like broader here. What we usually do is measuring the ICL up to the level. When I say total fluxes, is up to the level where it is detected. So in this particular case, the ICL, I didn't show the contours of the ICL, but the ICL was measured until up to a contour or within a contour that it was going like around here. To measure, to exclude all these areas where the noise or the sky background is dominating the ICL. That doesn't mean that there is not ICL outside this contour. There is, but is the limit where we can reach given our observations. And also these kind of features that you with a very good eye saw there, these features, there are a lot of low surface brightness features in the images, correlated noise, some kind of straps or strips or even nearly moire effects in the low surface brightness universe that are always present in those images. All of them are sources of contaminations. Because of that, ICL fractions usually have high error bars, because the ICL is the ICL measurement is super delicate and is polluted with a lot of sources, and this would be one of those. For example, we cannot assure to certify totally that there is no light coming from the star contaminating the ICL here either. So this is all including the error bar budget.
Thank you so much.
Thank you to you.
Thank you. Andres?
Hi, Yoli. Thank you for your talk. This is Andres Del Pino. My question is, well, I'm a bit puzzled by the excess of F and A stars in the, yes, exactly. And then later by the shift on this bump for the other redshift. Is there any, I don't know, could you elaborate a bit more? It wasn't clear to me what would be the origin of this bump.
Well, in fact, I didn't say anything because we still don't know. For the intermediate redshift clusters, we have the advantage of these other works that studied the stellar populations in the ICL. They indeed saw this excess of A and F type stars in the ICL of this particular sample of clusters that we later have discovered that appear for other clusters at the same redshift. But for these high redshift clusters, we don't have this study to give us some light to explain the presence of the peak. So we still don't have an answer for that. That's why I put there in preparation, because we are trying to know what's the origin of the peak for these high redshift clusters.
Okay, thanks.
Thanks to you.
Any more questions? So I had one question about the break you mentioned that you assume right now in the profiles of the BCG and the ICL. So how is there any observational evidence? Do you know any paper that actually can show that such a break actually exists, and in practice how the BCGs and ICL in different clusters behave in that regard?
Yes, well, the point is that we do know that this break exists because of this kind of studies, these dynamical studies. We do know that there are indeed two different compositions there, let's say so, or two different surfaces, which behave differently, dynamically speaking. We assume that photometrically we could see that in some way. And for example, when we tested it against simulations, although, for example, I didn't mention that before, but the green profiles here in the simulations are the composition of the BCG plus the ICL. So let's say that by eye, you don't see any break. But this break somehow is reflected in the curvature parameter. Moreover, when we compare, for example, for this particular case, we didn't compare this in many cases because there are a few studies of the ICL and its dynamics. But when we compare the break as outlined by the curvature parameter with the dynamics, they were very, very consistent. In fact, much more consistent than with other methods that were previously developed. But not only that, we also saw that the shape of the ICL, not only the boundary, but the shape was kind of similar, or very similar, in fact, with the findings using dynamics. So it's an assumption that seems reasonable, and when we tested it, it worked. But not only that, I've seen recently works that use this curvature parameter to differentiate the BCG and the ICL, but in one dimension, because it's easier to do that in 2 dimensions as we do. So they use this curvature parameter for 2 things, for the separation of the BCG and the ICL. I've also seen works using that to separate now the bulge of the BCG or the bulge of a galaxy and the disk, also in 1 dimension. And there is another recent work that has adapted this technique of the curvature parameter in 1 dimension to find the limits of the ICL in a very, very, very deep and spread observation of a cluster. And they have found that using this curvature parameter, and again, one of the points where its value is highest, they can find like the limits of the ICL, which match with the splashback radius of the dark matter halo associated to the cluster. So it's like there are a lot of evidence, and a lot of works are like somehow adapting this technique to one dimension because it's easier to do it. And this curvature parameter is showing a lot of let's say breaks in different things: bulge and disk in galaxies, BCG and ICL, limits of the ICL and splashback radius of the dark matter halo associated. So I don't know, there is a world out there to discover.
Yes, exactly. Very nice, thank you. So any more questions? No more on this side? Okay, so thank you very much, Yoli. It was a really nice review of the interesting method and the nice results, the exciting obvious readings. And thank you, and congratulations on nice work.
Thank you very much.
Okay, so Juan had to do some observations, so he went to his room. Now I'm not sure how to close the system.
I think that you need to stop recording first.
Oh, you're right. Where is the It's using some kind of, okay, I'll just see if I can exit. Where is the recording? Okay, I'll just try to see. Okay, I think I'm gonna exit. If I do, then bye. Okay.
Okay, thank you. Bye bye. Okay. I think you're mute.
Okay.
Okay.
Now she can hear us.
Okay. Thank you. Thank you so
Thank you
much.
very much. Thank you very much.
Thank you very much, Julie. I had to go because I'm remotely observing in Keck now. It
No,
turns
no
out that
problem.
nighttime in
problem.
Hawaii is daytime here, and by chance.
Good observations for you.
Thank you very much. Thank you for the seminar.
Thank you.
Thank you. Bye bye. See you.
Uh,